This was man's first great discovery, fire. The earliest man had only one way of getting the energy out of plants, and that was by eating them. And with the discovery of fire, he gained an enormous advantage over other animals. He learned how to turn night into day and winter into summer. In fact, that man was the first scientist. Strange breed, aren't they, scientists? Let me remind you of what Gulliver said about them when he visited Laputa, and perhaps somebody would you like to come and read this for us, this little section? He was visiting the Academy of Science in Laputa, and he met a scientist. What's your name?
Christopher.
Christopher, if you read from there to there.
The first man I saw was of a meagre aspect, with sooty hands and face.
Scientist.
His hair and beard long, ragged and singed in several places. His clothes, shirt and skin were all of the same colour. He had been 8 years upon a project for extracting sunbeams out of cucumbers, which were to be put into vials, hermetically sealed, and let out to warm the air in raw, inclement summers. He told me he did not doubt in 8 years more he should be able to supply the governor's gardens with sunshine at a reasonable rate, but he complained that his stock was low and entreated me to give him something as an encouragement to ingenuity, especially since this has been a very dear season for cucumbers.
Thank you very much, Christopher. Well, that scientist was a bit of a nut because, it had all been done before by the man who discovered fire. And cucumbers don't burn very well anyway. Let's have a look at the first fire that man used to produce his heat and his light. We have a nice selection here. Perhaps one of you would like to come and light a few candles for me. Would you like to come? Would you like to come and light the candles for me? The ones that aren't already lit. What's your name?
Bridget.
Bridget. Well, there's a taper. Would you like to be lighting those? Probably the first light that man used was a brand picked from the fire, and then some man would notice that when he was cooking his meat, the fat dropped down and a bit of moss in it produced a lovely flame. And so he discovered the oil lamp. This is one of the first oil lamps, and lamps of this kind were in use over 15,000 years ago. They're found in the caves of Lascaux, and you see all it is just a hole in a piece of stone, some mutton fat, and a bit of taper, moss or wick, which keeps it alight. Another very early kind of lamp, which is just a light here, was the shell lamp. These have been used for well over, for thousands of years, certainly. Have you done that? That's lovely. Thank you very much, Bridget. And they gave a pattern to many other later types of lamp. This lamp, you hardly believe it because it's in such good condition, is 3,000 years old. It was discovered in an Egyptian tomb, and like many of the lamps here, it's been lent to me by the Science Museum, where you can see a much bigger collection of these things. You see how it's a shell. It's made of pottery, but it's a shell, and here's one you must have seen many times, a Roman terracotta lamp, an improvement slightly with a top over it so that it doesn't spill. This is called a cruzy. It's got a drip tray. They were been in use for hundreds and hundreds of years and were still in use until recently. You see how they're all patterned in the same way, burning oil or, or animal fat, which some of you can probably smell. These are Indian lamps. the same design. These are still in use, still in use as ashtrays, but they're still in use for ceremonial occasions. You see how prettily they burn when you have a lot together like this. This is becoming a bit more modern. This is a whale oil lamp. Whale oil began to be used in the 18th century. It was used less by about 1830 or 40 because it became expensive. And finally, we get to the modern type of oil lamp with all sorts of fancy adjustments, which are very necessary anyway for adjusting the wick, and very wide wicks and a glass on them and so on. And then the other kind of lamp developed, no doubt, from the taper, the brand that the man picked from the fire, is the candle and the taper and the rushlight. And here are some examples of those. These are nice old medieval stands which have, this one will adjust up and down. You see, this is a Japanese one which folds into the pocket like this. They have various adjustments for height. This one goes up and down as the candle burns. This is a nice one, an old one. This is a bedside reading lamp, and just as today, when you can pull the switch to put the light out. If you don't want to get out of bed when it's cold, you just put it out like that. Now I wonder whether you can guess what this one is. This is a rather nice holder with an adjustable height for the candle. Do you know what that is? That was used, that's a Victorian gentleman traveller's lamp, for reading lamp for use on railway trains. And you just pin it into the seat of the railway train like that and read away, if you can stick it in. And then, of course, when you get off at the station, you blow it out and put it in your pocket and burn a hole in your pocket, probably. Well, those are some of the lamps which have been developed, and all of those used the products of vegetables and animals. They use coconut oil and olive oil and fat, beeswax and fat from animals and so forth. And it was the developments were remarkably slow, and it was only relatively recently, really in the last 100 years, that the fossil fuels, gas, oil and coal took over. And I can show, let me show this to you on this card, this graph here. On this graph, I've plotted the percentage of the fuel against the year. Now, this isn't the amount. The amount increases enormously over this period. And, but you see that until 100 years ago, the principal fuel for heating, lighting, everything used by man was wood and animal dung and oil, vegetable oil and things like that. By 1900, coal was predominant. 80 or 90. These are figures for the United States, but they're very similar in Europe. And now, of course, oil and gas have taken over completely almost from coal as a percentage. We still use a lot of coal, of course. We use much more of these things. But the percentage of these fossil fuels, oil and gas, has increased enormously. Of course, because they were discovered relatively recently. Petroleum was only discovered about 1860 in the United States. This little brown bit at the top is other sources like wind and water and nuclear and so on, still only 2 or 3% of the total. We've come to rely on these fossil fuels, which are really made by sunbeams through the plants. They're fossilized plants. We've come to rely on them so much in modern life that we just couldn't exist without them. They're almost as important to us as food. And so it's important that we should look at them and see what they are. Let's have a look at coal first, which really made the Industrial Revolution possible and put Britain ahead of most other nations because of its coal resources. Well, coal starts by being plant material. cellulose particularly. Is cellulose still with us? Is there somebody with... There's cellulose. Remember, that was the cellulose molecule we saw before. Now, you see there's a lot of oxygen in that. See those red atoms? Okay, thank you. And by fermentation and so forth, that disappears. Just to show that coal is made from plants, you can see fossils in it very readily. This is a bit of shale from just above the coal seam in Barnsley, and you see very clear and very beautiful patterns of the ferns, which in the swamps decayed and formed, first of all, a matted mass of organic material, which we call peat. And then, as more landed on top of this, it became compressed into brown coal, rather light-colored coal, and more compression, more loss of carbon dioxide and some hydrogen and methane, and we get the coal that we're so familiar with in Britain, which has been the lifeblood of our industry for so many years, bituminous coal. And finally, if you leave it long enough, you get anthracite, which is almost pure carbon. It's 95% by weight of carbon. Now, all those are fossilized materials from land plants. So how old do you think coal could be? What's the oldest coal we could possibly have? Well, do you remember what I said about when life first came to the land from the sea? 2000. It's about 400 million years. So the oldest we could possibly get would be about that. And in fact, the British coal deposits are about 300 million years old, most of them. Coal is still being formed, but most of it was formed in the Carboniferous period, which is just under 300 million years ago. Right, now what about oil? Well, oil, we don't know quite so much about. There's some argument still about oil, because of course you don't get fossils in oil. But what you do find about oil is evidence, very clear evidence, that it comes from living things, because it is optically active. Now, do you remember what I mean by that? Remember, it rotates polarized light, and that's a characteristic, isn't it, of living things? Remember, when we make them in the laboratory, they don't. And so it's quite clear that oil comes from living things. And it is almost certainly, it's generally accepted, that it's made from living things in the sea. The settlement of minute algae and bacteria and so forth from the surface of the sea, they are partly oxidized as they die, like a compost heap. And then they can't get any more oxygen, and the bacteria work on them and again push off the carbon dioxide and eventually give you something with just carbon and hydrogen as the main components. Let's have a look at our great favorite oil field in the North Sea, because this is very vital to our economy now, isn't it? And it's of interest to us all. Here's the North Sea, upside down. There's the North Sea, and here at the bottom, the south, are the gas fields. But the oil field is this part here. The main oil fields are in this part here, and they're all in one rock formation, which the geologists call Jurassic, of about 150 million years old. That is to say, just about half as old as coal. The oil isn't as old as coal. Now, here is the Brent field. And the Brent field is the largest field in the British sector, and it's of particular interest to us because it's only just come on stream, and it's going to produce the goodies for quite a long time and in large amounts. So let me show you some bits of the Brent oil field. Here is a bore taken from the bore down to the Brent oil field at 8,000 feet. And this is called the source rock because this is where the oil is formed. All this organic matter gets compounded with inorganic matter, and in here you get the lines of organic matter which are compressed and at high temperature lose more oxygen and become oil. And the oil is squeezed out now into the reservoir rock. And this is the reservoir rock. It smells of oil. This was taken from 8,500 feet down in the Brent field. And it smells of oil. And this is what we mean by an oil reservoir. I used to think an oil reservoir was a big hole full of oil, but it isn't at all. It's rock, and the oil is in the rock. The rock acts as a sort of sponge, and it's then at very high pressure. And when you bore down, the water and the water forces the oil out, and up comes a lovely spout if you're lucky. Well, that is the reservoir from which the oil is extracted, and here is some of the lovely stuff. From the Brent oil field. It's beautiful oil. It hasn't got very much sulfur in it, and when you distill that, you get petrol and paraffin and candles and all the good things that we need. So that is the coal and the oil and how they're formed and so forth. And now we must look at what they are chemically. Let's have a look at that cellulose once more, can we? Now, that's a carbohydrate, remember. It contains 1 carbon to 1 water molecule. And it has a lot of oxygen in it. Thank you. The oils are hydrocarbons, which are like this. They have carbon, the black, you remember, and hydrogen, the white, tied together like this. And those are hydrocarbons. They've lost their oxygen. And they come in all sizes. The smallest size you can have of a hydrocarbon is this molecule. It's a slightly different model from the one you saw before, but can you tell me what it is? Methane, yes. It's CH4. And then they grow to bigger ones like this. The smallest one, I suppose, is hydrogen, because they change by units of CH2, and 1 less CH2 than methane is hydrogen. Well, here's some hydrogen, a gas like methane, and that, as you remember, reacts with oxygen or air. So, and that is the combustion reaction, which carried out incidentally in a way which we don't usually want. We want it to burn rather more comfortably, like this. And this is now This is North Sea gas, because it is North Sea gas. This isn't. It's coming from the tap. Sometimes we have to use the old coal gas. This is North Sea gas, and that is mainly methane. That's mainly this molecule. That would explode. In fact, it explodes more violently than hydrogen. But we can also burn either of them as a flame. Now, here's the next one that I'm going to talk about. That's butane. Methane, ethane, propane, butane. That has 4 carbon atoms. And that's useful because that is now it hasn't quite made up its mind whether it's a gas or a liquid, when compressed, it's a liquid, and when released to atmospheric pressure, it's a gas. So it's useful to be able to carry it about like that. Now we go up some more, and this is 12 carbon atoms. And what do you think that is? Have a guess. Petrol. That's ordinary petrol. Round about 12. I mean, petrol is a mixture, but that's round about 12. And will it light if I put a match to petrol?
Yes. Yes.
Yes. Will light. Burns quite happily. Let's go up some more. This is, did I say that's 8, isn't it? Did I say 8? That's 8.
12.
I said 12, I'm sorry. That is 8. That's octane, who heard of the octane number of petrol. It's about 8 carbon atoms. Now this is 12. And that is paraffin. That's paraffin, which looks just the same, except for its color, which has absolutely nothing to do with it because it's colorless. These are just dyes put in by the manufacturers so that you know what it is and also who manufactures it. Now, will paraffin burn?
Yes.
Yes. weren't.
Ah.
Paraffin, that's why you see you had to put a wick in those lamps. Paraffin doesn't burn. Not like that, because it's a liquid and it doesn't vaporize. It's only the vapor that burns, and it doesn't vaporize as easily as the petrol. Now, what do you think this is? This has 30 carbon atoms. That's what that is. The candles that I showed you before, at least the candles that were used by the early people who used candles, were made of mutton fat, or tallow as it's called, animal fat, or if they were very rich people, they bought beeswax, which smelt nicer. But nowadays our candles are made from paraffin wax, taken from the paraffin oil, and that's what it is. It looks an oily sort of molecule, greasy, doesn't it? And it has about 30 carbon atoms. That's paraffin wax, and of course that burns nicely as a candle. Now that's about as high as you can go by taking it out of the ground, but chemists can do more, and they can string together hundreds. I've had to go to a smaller scale now. I also had to borrow my wife's beads. But that on a smaller scale would be about the length of a smallish molecule of polythene or polyethylene, because all polythene is candle wax made by man with longer chains of carbon atoms, and so that would have about 100. Now these all seem to burn very, very differently, but it's partly because some of them are gases and some are liquids and some are solids, and their chemistry is very much the same. For example, paraffin is a liquid. If it were a solid, we could make it burn like paraffin wax. And in fact, Mr. Coates has made one for us. We could perhaps get rid of that one. There's an ordinary candle made of ordinary candle wax with 30 carbon atoms. Now, we've also made a candle of polyethylene. There's a candle of polyethylene with over 100 carbon atoms in its molecule. And we have, Mr. Coates has just made a candle of, candle of paraffin, rather. I don't know whether I can do this without knocking it over. And the reason it's so cold is that he's had to freeze it down in liquid nitrogen to make it. But you see he's been successful. And now we have 3 candles which look very similar, and they're made of very different substances. That one burns all right. This one doesn't burn very well at all. The wick will burn, but then the candle will go out. Remember, this is made of polyethylene, and to make that burn, I've got to get it really hot. I get it hot in this Bunsen burner and try and make it burn to show you that it does burn. You see, it's such a big molecule that it doesn't melt very easily, and it doesn't make gases very easily either. And so to get it going, I really have to decompose it. And of course, if I then do decompose it, I can pull it out into long fibers like this, you see? See these long fibers coming out here, like this? That's polyethylene. And now they will burn because the air can get at them very much more readily. So I pull those fibers out, they burn quite well. But you wouldn't really buy that as a candle, would you? Well, they all burn chemically in a very similar way. This is really getting out of hand a little bit, so we will take that. Or we'll have that one lit again, perhaps. Now, I want to ask now, then, why is it that, although the chemical reaction here is just these compounds with oxygen in the air making carbon dioxide and water, well, why do some explode and some give nice flames and some not burn at all? Well, the reason is, the first thing we must consider is that it's a chemical reaction of a fuel with what? oxygen, the oxygen in the air. And you must have both there. They're just as important. Now, unless you have the two can get together, then nothing will happen. Oxygen will react with almost anything. It's a terrifically reactive compound. It'll react with metals if it can get at them. And in fact, we would have no metals on the Earth if oxygen could get at them. So why do we have any metals? Why do we have spades in our garden which don't fall to bits? Well, they do fall to bits. They oxidize quite rapidly. You see, this is a rusty spade, and now the rust, the iron oxide, is protecting it from further attack by oxygen. Aluminium does the same, and lead, I think, lead does the same. I have a lump of lead somewhere, but there's aluminium, which looks fairly shiny, but it's got a coating of aluminium oxide on it. And the unique thing about carbon as a fuel is that its oxide is carbon dioxide, and carbon dioxide is a gas. And so when it burns, the gas comes away and leaves the clear carbon underneath, and everything can proceed quite readily. Lead is the same, and lead forms an oxide on its surface. But if it's finely divided, instead of being a big surface like that, if it's finely divided into little particles, then you see it burns very readily. That's just finely divided. It's metal lead, and it spontaneously burns in oxygen because it has much more surface, and the oxygen can get at it. Well, that's the crux of the matter, and there are many ways in which we can make the oxygen and the fuel get together better. For example, we can mix the fuel with the oxygen. Now, you can't keep oxygen. If it's a solid, you can't keep oxygen in it as oxygen. But gunpowder, this is gunpowder, is made of, it doesn't explode, it burns fairly comfortably. Gunpowder is made of carbon and sulfur and an oxygen-containing compound like potassium nitrate. You see how very difficult it is to make it burn. And it burns fairly quietly as long as there's plenty of space for it. If you pack that into a cartridge, it doesn't burn so quietly. Here's another plastic fuel. Here's another solid which we can burn, and this is called plastic propellant. It's made of rubber, and the rubber is mixed with an oxidizing substance, which in this case is ammonium perchlorate. Now, there it is. And that's what you put into rockets as a solid propellant. Rockets, to send them up into satellites, is just rubber with the oxygen in it, you see. So that it doesn't need, there isn't much oxygen up there anyway. And furthermore, if you're going to fire your rocket, as you do sometimes, from a submarine, then it has to be, here's some of this plastic propellant, which I've just put on the end of a fuse. And if I am going to fire my rocket from below water like that, then it's got to be self-sufficient in oxygen. So I light the fuse. And if the fuse doesn't go out when it hits the water, it should be able to light the rocket propellant. Now it's reached the propellant. There it goes. Well, so that's jolly useful for Polaris missiles if you want to make a Polaris missile. Another thing you can do is to, instead of mixing two compounds, one with a lot of oxygen and one as a fuel, what you can do is make them all into one compound. Let's see cellulose once more. You're doing a good job this afternoon. Cellulose, here we are again. Now, that cotton is cellulose, and that burns quite well, but it doesn't have, it has a lot of red oxygen there, but it doesn't have enough to burn all the carbon and the hydrogen. Thank you. If we turn that into nitrocellulose, put nitrate groups, NO2 groups, you give it much more oxygen. There's enough oxygen almost exactly to burn all the carbon and all the hydrogen to water and carbon dioxide. So this is nitrocellulose, and you see that burns differently from cotton. And in a short time, it is all now carbon dioxide and water around the room. Now that again, if that's packed into a small volume and compressed, it is used as a propellant and can be very dangerous. Well, those are the processes. The important thing I wanted you to realize then is that it's the getting together of those two reactants which determine whether it's an explosion or a nice steady flame or a combustion or what happens. It's very important to know the difference, isn't it? Just a word now about what the chemical reaction is. You know what it is with hydrogen and oxygen reacting with water, but how? How do they do it? When that bang occurs, what happens? Do the molecules come together and just make what?
They're going out.
They're going out? Well, they break up first. I think that's probably what you mean. Let's have a look at them here, just a bit more. Thank you. Here we have some oxygen and hydrogen molecules. You know which are which, don't you? Red, oxygen, white, hydrogen. Now, when I put a match to them, they don't react at room temperature. If I just bang them together, they don't react. But if I put a match together, I might split one hydrogen atom into molecule into two atoms like that. And now, that can react with oxygen like this and form an oxygen atom and an OH. And OH is not a stable substance. It's extremely reactive, and that will react with another hydrogen like this and form, what's that? Water. And the oxygen can react again with that hydrogen, and this can react again with that hydrogen and form another water. Now, what I want you to notice is, firstly, we're making the product water. Secondly, we're doing it in a lot of steps. But one other thing, we started with when I put the match to it, I made two hydrogen atoms, didn't I? And now I've got 1, 2, 3, 4. And these are continuing the chain. It's these which carry the chain forward. So if I've made 4 from 2, I'm going to get an explosion. It's called a branch chain reaction, explosive chain reaction. Now, what about petrol? When I burnt petrol, I need many, many molecules of oxygen to burn one molecule of petrol. Do they all come together at once? And no. They couldn't possibly. Not in a million years would they come together. Here's petrol. That's an octane molecule with 8 carbon atoms in it, and there are 4 oxygen molecules waiting to pounce. And if I heat it up with a match, they will do something like this. They might attack there and pull that hydrogen atom off, so, and then an oxygen molecule may come along, it's a molecule, comes along under there, so, and that might then pick up a hydrogen atom from something out here, and then break off this radical, this OH, and now that molecule can break off, because it's a stable molecule. I wonder whether anybody's such an organic chemist that he knows what that is. It's acetaldehyde. And it's a stable molecule, so it can break off, leaving another end here, which has a spare prong on it. And so it goes on. Now, I've only just begun. And there are many you could have attacked at other positions. And there are several hundred steps before the whole combustion is complete and before you've got carbon dioxide and water. And all those occur in an incredibly short time. If you look at a Bunsen flame, or any gas flame like this, you see there's a cone. Inside the cone is unburnt gas. On the outside of the cone is the burnt gas. And the cone is only a few millimeters thick. And the gas gets through that in a few thousandths of a second. And yet, in those few thousandths of a second, all that has happened. All those reactions have occurred. And that the 100 or more steps have occurred in that time. Well, it's very important to know how these reactions take place so that we can burn these valuable fuels that we have more efficiently, and so that they don't go bang when we want them to go pop, or when we don't want them even to go pop, we want them just to burn as a nice steady flame. We nearly stopped having any coal altogether around about 1812 because there had been so many disasters in the mine. The mines, you see, along with coal, is formed methane. And methane, of course, as we've seen, is very explosive. And in 1812, there's a terrible explosion in the colliery at Gateshead on Tyne. Nearly 100 men and boys were killed, and this was almost the last straw. Men were beginning to say, we're not going to go down anymore, it's too dangerous. And this was a real crisis. And so a committee was formed. They said, what shall we do? And some bright member of the committee said, I know what to do. Send for Sir Humphrey Davy. Now, Humphrey Davy was a resident professor at the Royal Institution at this time, and very, very famous. He'd made many great discoveries, and they asked him, please, would you solve the problem? And Davy did a wonderful piece of science, applied science. He didn't just say, oh, well, I'll try a few things and see whether one works. He sat down and said, now, what is the problem? He went to the mine. He found out what the gas was, found that it was methane. And then his problem was as follows. The only kinds of light known were practical lights that could be taken down, were flames, were candles and similar things, candles and oil lamps. Now, if you go down into a mine which is full of coal gas, as Bill has just filled this one, and you go down with a candle, it isn't nice at all, and you won't survive. And yet you must be able to see what you're doing. So what could Davy do? How could he possibly solve this problem? Well, he began to reason that to do any damage, a flame has got to travel. It's got to be propagated. If you could just keep it in one place, it would be all right. And he studied how flames propagate down tubes. Here is this we can think of as a passage in the mine down which men go. And here is a large chamber in the mine. And suppose it's full of coal gas, and I take down a light. Mr. Coates has filled it with coal gas, and I'm going to light it at this end. Here, I'm going to light it now. Well, that may be amusing as a demonstration, but it ain't amusing if you're down in the mine. And that's the problem that Davy had to solve. Now, this is a little experiment that really you probably done yourself, and Davy knew about, and which really describes the principle of what he did with his miner's safety lamp. I filled this can with gas. It's got a hole at the top and a hole at the bottom, and now it's burning with a flame which you might be able to see just about in this can. And the flame isn't going through into the can. It's stopping at the hole because the metal is cooling the gas, you see? And you'll see the flame get smaller and smaller as it burns faster and faster because more and more air goes in. Now, Davy said, why don't we solve the problem this way? Here's all these are the safety lamps that Davy actually used. He said, let us put our candle in this and make the gas go through tubes like this, so that the gas can go through, or the air can go through, and not the flame. And then he thought of a better idea eventually and said, well, why don't we just use gauze? Because that has little holes in it, and maybe that'll cool the flame down so that it doesn't go through, but the air and the gas can go through anyway. This flame has extinguished itself, I think, has it? No, it's still going. It's very, very small. Very, very small. Well, all right, so we can try that experiment on this tube. He took, to put into this tube, there it went, you see? That's what happens when the mixture ratio is such that the flame speed is great enough to go through the hole. It's greater than the gas coming up. Now, Davy said, let's take some gauze, some wire gauze, and put it into this tube, which has been propagating our flame pretty well up to now, and I'll just bind it round with tape so the gas can't get out. Now, the gas can get through that gauze, obviously, because Mr. Coates is filling it from that end, and the gas is coming through to this end. And now we're going to do the same experiment and see what happens, see whether it'll blow it up. All right? I'm going to light it now. Here. See? Stopped at the gauze. The gauze is going red hot. Okay? Gauze was absolutely red hot, but it didn't go through. Even though red hot, it didn't go through and blow up the chamber. So, Davy had the answer. He had this answer in a matter of a couple of months. He was helped by Michael Faraday in this research. He said, all we have to do is enclose our lamp in, whether it be an oil lamp or a candle or whatever, just enclose it in gauze like this. And now I can go down the mine safely with my Davy lamp, fill the mine with coal gas again. I go down, I can see perfectly well through this, and let's see whether we blow it up. No, we don't blow it up. And what is more, you do see the gas burning inside the lamp, you see? There's the gas which I'm putting in from outside, burning inside the lamp, see? But not in the chamber itself. And that was a great thing, because not only did it solve the problem, but even today, these are used because they smell out the gas. You can see the flame change when you have gas there. It's better than canaries. Anyway, canaries don't like going down mines very much because it kills them. This is a way of testing for the gas. And so Davy never patented it. He gave it to the world. It was a great invention. It's there are many sort of improvements on it, some of them used today, some using oil lamps like this. But it saved many lives, and it makes it possible for us to have coal and oil, well, coal in particular, as still today. But because it's so dangerous, because they're so expensive, we should use them very, very carefully. We should try to use them not extravagantly, and if we want to get heat out of them, in any case you pay so much for them that you're not going to use them very extravagantly, are you? But if you're going to use them efficiently, you must know how heat gets around. If you want to heat a room, you must heat the room and not the garden. And to do this, we must understand how heat gets around. Well, there are three ways in which heat gets around. The first is conduction, and I can illustrate that by asking one of you, perhaps you would like to put your right hand on, this is the famous hat we made of polyurethane. Put your hand on top. No, I just want you to feel it. On the top of that, and your other hand on the glass. Now, what's the difference? Which is hot and which is cold?
The glass is cold.
What? Which is cold? Put the hand up which is cold. Very cold, isn't it? And that's hot. All right, let's try another one. Here's my coat, and here's some metal. Would you like to put a hand on each of those and on the wall there? Yes. Which is cold?
The wool seems colder than the actual metal, which seems slightly warm to me. I don't know,
Well, maybe.
Someone's been holding it.
Maybe you're right. Would you put a hand on each of those and tell me which is cold?
That one.
Yeah. Which would you say?
That one.
Yeah. I think there's. Well, we've got a majority. No, I think he was probably trying to explain something more subtle than what we're going to say now, because there's no doubt about it, which feels cold. But they are the same temperature. I was asking which feels cold, not which is cold. They must be the same temperature because they've all been in the room all the time. Must be exactly the same temperature. One feels icy, the metal feels icy cold. You can feel it afterwards if you think he's right. It feels icy cold. Now why? And the answer is that you are warm, your blood is at 37 degrees centigrade and much hotter than the room and much hotter than the metals, and so the heat is conducted away by the good conductors and it feels cold. So that's one way that heat gets around. Now, the second way that heat gets around is by radiation. We talked a bit about this in the first lecture. You learned how bodies radiate and radiate more the hotter they are. So let's have a look at radiation now. Here is a reflector, and we're going to put a hot body there. There's another reflector up there, which should focus it onto a black body up there. And now Mr. Coates is going to bring in his hot body, which is a red hot body, which he will put there in the middle of that reflector. And there it goes. It's reflected there onto the black body, which had a bit of combustible material in it. And how was the heat transmitted from there to there? Not by conduction, was it? But by radiation. So that's the second way. We can, here's an illustration of both conduction and radiation together. Here I have some unripe apples, 2 unripe apples. And of course, if they were real apples, we would need a sunbeam to ripen them, but they're not real apples, as you can probably see. And I have here an electric radiator, which is just coming on, isn't it? And I'm going to put my apples in front of that, and I think you may see that they ripen. The material that's on here is not apple skin, but it's a material which changes its crystalline form when it gets hot and becomes red. And so I think you can see a little blush appearing on the apples now as they ripen. You see them ripening nicely. And how is that happening? It's happening by radiation from the electric fire, and then by conduction through, isn't it? Because I'm heating the back, and it's getting through and heating the front. And I don't recommend it as a means of ripening real apples, but it illustrates conduction and radiation together. Now, thirdly, there is another way in which heat gets around, which is quite important. And this was discovered by the founder of this institution, Count Rumford. Rumford was very interested in heat and how it got around for practical reasons, which I'll tell you about in a moment. And he was puzzled, he was really worried by an abstruse scientific problem, which was, why does my apple sauce always stay hot on my plate when everything else gets cold? It's a very tedious fact. That your apple, have you noticed this? You burn your tongue on the applesauce and everything else has got cold, but the plate certainly. Now, why this is such a puzzle is that applesauce is nearly all water anyway, and water cools quite quickly. So it's nothing to do with conduction or radiation. And Rumford solved the problem by being very observant and noticing one day when he had a little tube of liquid on his desk and the sunbeam was coming through and shining onto it, he saw bits of dust circulating, and that was convection. And let me show you convection. Here is a tank of water, and we'll shine some light through it so that you can see it on this screen. And at the bottom of the We drop the lights. If at the bottom of the tank, we have a wire here. Now I'm going to heat the wire. Mr. Kurt's going to heat the wire electrically. And as I do so, you see the hot water rising. If we could drop the lights, please. We can see the hot water rising there. Now we can see it nicely. The hot water rising because it's lighter than the cold water. And when it gets to the top, it comes down again and circulates. And that's called convection. He's going to put a bit of dye in so that you can see it better. And that illustrates very nicely what Rumford saw. And clearly, you see, if this were apple sauce, it couldn't happen, could it? Because the apple sauce is all lumps. And it would just get hot down there, but the apple sauce couldn't circulate round. And that's why apple sauce stays hot, because it can't get the heat to the surface. So that was convection, and those are the three ways in which heat gets around. And Rumford used them to apply it to the common purposes of life. Rumford was born in America. He was called Benjamin Thompson, and he was made a count in Bavaria for very important work he did in helping to feed and clothe the poor. Munich was full of beggars and the army was in rags, and Rumford solved this problem by applying science to their poverty. He studied nutrition and tried to work out the cheapest food that you can possibly get to feed people, and discovered Rumford soup. And, you know, times are so hard these days that I thought you might like to have the recipe for Rumford soup. Here it is. If you like to make a note of it, you take 4 firtles of pearl barley and 4 firtles of peas and so on. Now, you may not know what a firtle is, but it tells you here what it is. A firtle is a 12th part of a schäfel. So now you'll be all right. And if you don't know what a schäfel is, maybe you don't know what a schäfel is. The Bavarian schäfel is equal to 6 31/100ths of a Winchester bushel. So now, with a system like that, who needs metrication? Well, the Rumford soup, of course, wasn't the main thing that Rumford did. Otherwise, I wouldn't be spending all this time on him. He applied these principles of heat transmission from one place to another to cooking. He was very concerned about the inefficiency of stoves. He said the present-day stove heats the cook and not the food, and it did. And he used enclosed stoves, and he used the principles of conduction, convection, and radiation to improve things. He was responsible for an early form of pressure cooker and of coffee percolator. And here's an example of conduction, the use of conduction. He developed flat-bottom pans so that you could conduct the heat to the soup better. Here is an example of radiation. He developed luster jugs so that the heat, if you want to keep something cool, the heat would be, heat's reflected just like light, the heat would be reflected away. And then an example of convection, perhaps his most famous contribution, was to stop fires smoking. It may seem trivial, but if you've sat by a smoking fire and have no alternative, then you won't think it trivial. Now, if you want to make the smoke go up the chimney, what do you do? Make the chimney bigger or smaller? Yeah, you make it small. It's not obvious, is it? But you do. And Rumford introduced this idea of making a very small throat. Because what happens then is that it's heated and the hot air rises. And that stops the cold air and the smoke coming down the chimney. And it was to Rumfordize your house was very well known at that time. And here is a contemporary cartoon by Gilray of Rumford enjoying the comforts of a Rumford stove, warming his bottom on the fire of the Rumford fire. Well, he wasn't the only one who applied these principles of transmission of heat. A rather different example is supplied by another professor here, Sir James Dewar. Now, Sir James Dewar was particularly interested in liquefying gases. And he was the first one to liquefy air in quantity. Now, other people had liquefied air, made liquid air. It's not too difficult. But the trouble is, it was just a mist, and they couldn't keep it. Because as soon as they poured it into an ordinary vessel like that, it evaporated, boiled away extremely quickly. So Dewar developed the Dewar flask, or the vacuum flask. And here are 3 stages in the development of it. I'll pour some liquid air into each of them so that we can see what happens, and then I'll explain how he was using conduction, convection, and radiation principles to keep the liquid air cold. Now here, he's just using double glazing. You use double glazing to stop convection and conduction, don't you? There's still air between, but he's using double glazing. Here, he now says, but the air, you can see the difference already, how this is misting over. He said, but the air is still convecting and conducting, so I'm going to take the air out, and he evacuated it. That's why it's called a vacuum flask. And now he's killed conduction and convection pretty completely, but he's still got one thing left, which is radiation. And so what do? You silver it, like Rumford's lustre jug. You silver this. He tried gold and other things, but settled for silver in the end. And that stops the radiation. And now you see, although this is misted over, and this one is not, but is still boiling, this one in here has practically stopped boiling. So that's another application of the principles. And we can apply these principles, we must apply these principles to our fuels. When we pay nearly £1 a gallon for petrol, what we're paying for is 50 million calories, and we must use those calories efficiently. And we can do so in our houses by wrapping the houses up to prevent conduction, convection, and radiation. I'll have a little to say about that next time. And to our bodies as well. If you were a black body and you were in outer space, you would be radiating 1.5 kilocalories. 1.5 kilowatts. That's the same as 1.5 bars of an electric fire. And if you're not a black body, you needn't be very happy about it, because it's pretty well the same if you're a white body. But, of course, the skin is not at the same temperature as the blood, 37 degrees. And we wrap ourselves up. And we must wrap ourselves up very, very carefully. Otherwise, you wouldn't survive very, very long at the temperature of the night outside. We trap the air in our coats to stop the conduction and the convection as we go home. Otherwise, we wouldn't survive. Of course, we still lose a little bit, perhaps 50 to 100 watts we're getting rid of all the time. So we have to make that good from the fires inside. And if some of you feel that you haven't the fuel for the fires inside, our chef here is offering you Rumford soup. Would you like to try a little Rumford soup? Would you like to try some? Try a little Rumford soup. Well, Mr. Chef, this may be a scientific and an economic achievement, but it's a gastronomic disaster. There must be more pleasant ways of trapping the energy of sunbeams, and we'll look at some of those next time.